Welcome to this 21st lecture video for Physics 4A. We set aside this lecture set demonstrating more mixed problem solving strategies, now including the methods we introduced for the rigid body motion and static equilibrium. We treat universal gravitation very lightly, that is, not at all in terms of exam type free-form questions, although you have done homework questions and will answer some multiple choice questions later. We do this so that we can focus on conservation of energy, momentum, and angular momentum and standard strategy type questions, now updated to include a consideration of torque and angular acceleration. In this set, you will see more examples of static equilibrium analysis questions, calculation of rotational inertia by direct integration, another version of ballistic pendulum question, and a couple examples of objects undergoing rotation under a torque due to gravity. As we did twice before, this is not a comprehensive presentation of all the new types of problems that can now be solved. I only had 2 hours to cover what I thought would be most useful for you to see. I encourage you to try other problems on your own and also look at the additional problem solving videos that are available elsewhere in the course. So with that disclosure, let me start. 20 minutes is not a lot of time, so I'll be quick about it myself. So this is the question. It's saying static equilibrium is characterized by, it's giving us the static equilibrium condition. And then it's just gonna be a question of basically multiple parts. So consider what happens when only one of the two equilibrium conditions are met. And for this, how do you know that the net force is 0? So I think I can just type it in. We can figure out that the net force is 0 using Newton's second law and the property of a center of mass. The center of mass will remain at the same velocity, i.e. Start at rest and stay at rest, which means the sum of the total forces on the object must be 0, even if net torque is not. That's one. 2. What consequences result from non-zero net torque? The object will angularly accelerate about its center of mass from the rotational version of Newton. Second law. 3. What consequences result from, that was 2. 3. Is it possible to have a zero net torque with a non-zero net force? Yes. For example, if I push a block on a frictionless plane to the right so that it accelerates, but it doesn't rotate, then it is experiencing non-zero net force while experiencing a zero net torque. Its angular acceleration is 0. Alright, I think that's the full answer. Let's do part B. You attempt to push a box, as illustrated, with the coefficient of friction between box and the floor, and what maximum height can. So I have to do standard strategy. So let me start with and it's been a while since we've done standard strategy. So let me remind you of the 4 steps of standard strategy. The standard strategy says, step 1, you draw free body diagram. Step 2, you define coordinate axis. Now, with the static equilibrium, you gain certain bit of freedom here, which I'll use. It's step number 2 gets significantly easier. Step number 3, if necessary, break forces into components. Here, I don't think that will be necessary. And step number 4, finally, write down Newton's second law equation. Net force is equal to mass times acceleration, which will be 0 in this case. And also because we are dealing with the static equilibrium and rotation, you have to do this for rotation as well. Net torque is equal to rotational inertia times angular acceleration, which again here will be 0 because of static equilibrium. So let's just start with the free body diagram. So I'm gonna draw a box so that I can indicate the location where the forces are at. There's always gonna be gravity, so let's start with the gravity. I'm gonna treat it as acting at the center of mass of the object. And then I'm gonna have applied the force, which is gonna be acting at some height h. Let's say it's acting here, and I'm just labeling this as height h, capital H. And this is my F, apply the force. And you ask yourself the question, did I draw all the forces? Then you think about, okay, what are the possible sources of force? I drew gravity, and you look at everything that's touching the object. So my apply the force is touching, I already drew it. The only thing else that's touching the object is the floor here. So you must have contact force that's coming from this surface of contact. And whenever you have surface contact, you are basically going to be considering two forces, normal force and friction force. And here, because they gave us the friction coefficient, I guess we will have friction force. So let me draw friction force going this way. That's going to be force of friction. And when you draw normal force, this is where you have to be careful. So if you are tempted to draw normal force like this, just think your way through. Eventually, you are going to have to enforce these static equilibrium conditions. If you drew normal force like this, is it possible to enforce that condition? And I hope your answer is no, because it looks like when you add up all the forces, this apply the force will make it rotate clockwise. So I gotta think my way through, and it's asking what maximum height. So as the height of the applied force goes up, if I'm thinking of having a center of rotation, I don't know. I guess I could have my center of rotation here. Then as height goes up, the clockwise torque goes up. So I need to position my normal force to counter that as much as possible. And yeah. Both the torque to apply the force and torque to gravity. So I think my normal force, it has to be as far to the right as possible, so that for a given amount of normal force, my counterclockwise torque is as large as possible. So yeah, so that's my normal force. That's my step number 1. I think I've mentioned how drawing free body diagram, that's the step that takes the most thinking, most amount of time, most creativity. This is what I mean. You have to draw the forces correctly at the correct locations, and it really should take the most of your attention on this problem. So I drew 4 forces, and I think that's it. So I can do the define coordinate axis. That's gonna be super simple. I'm not gonna complicate it. Just x. Oops, let me just draw it a little bit easier. X and y. Just straight axis. I don't have to make it complicated. And I don't need to break any forces into components. Every single one of my forces are either horizontal or vertical. So all I now have to do is write down my Newton's second law equation, and I'll write the static equilibrium version. So my net force in the x direction is going to be the applied force minus the friction force. That's going to be equal to 0. Net force in the vertical direction is going to be normal force minus gravity. That's going to be equal to 0. And my net torque is going to be, let's say clockwise is positive and the counterclockwise is negative. Then apply the force and the gravitational force. Those are my two clockwise torques. So let's say it's going to be apply the force. My lever arm there is H. So it'll be H times apply the force. My lever arm for gravity, perpendicular distance to this, is going to be half of the width of the box. So it'll be plus half of the width of the box times the gravity, mg. And then normal force, it'll be minus the full width of the box times the normal force. And that should equal to 0. Good. And if you are wondering, so if you are wondering why didn't we use this lowercase h, let's see, do we have an explanation for that? I think it's fine. Sometimes depending on your choice of center of rotation, some dimensions don't end up mattering. I think we're fine ignoring that lowercase h for now. I mean, it controls where your center of mass, how high your center of mass is. But I don't know if that matters in this particular case. Without tipping over. I think we're fine. Normal force is all the way over here. Maybe was I thinking of? No, I think it's fine. So let's so this is the end of standard strategy, and I see that I have 1, 2, 3 equations. Let's see how many unknowns I have. So at what maximum height h? Okay, that's one unknown. I'm trying to figure it out. Can you apply a force Ff? Did they give us the Ff? I don't think it did. So I don't think we know the applied force. Do we know the friction force? We don't know the friction force. Do we know the normal force? We don't know the normal force. Now, we could use this equation to calculate n is equal to mg. If we do that, we know the normal force, and in exchange, we only have 2 equations. So either way, it's a wash. So we got either 4 unknowns and 3 equations, or 2 unknowns and 2 equations and 3 unknowns. Either way, it comes down to I need one more equation, and that one more equation is the expression for the friction force. That friction force. Since we are dealing with kind of maximum extremum situation, we'll say that's equal to the friction coefficient, which we are given, times the normal force, which we calculate to be mg. So that's going to be mu mg. So with this equation number 4, now we can find h here. So let's be systematic about this. I can solve equation 1 for applied force. My applied force must equal friction force, which is equal to mu mg. I can plug it in here, plug in normal force here. Then I think I'm going to have a single equation in terms of a single unknown. So h times apply the force, that's gonna be mu mg plus w over 2 times mg, everything known, minus w times normal force, mg, is equal to 0. Let me simplify this into minus w over 2 mg. And finally, solve for h is equal to, move this over, it's plus wmg over 2. Mg's cancel out from both sides. I guess that's nice. I was expecting a sort of a geometric answer. So highest height can be is w over 2 mu. That's the highest height you can apply the force and be okay. Oh, and I think I know that's where this small h matters. So it's a matter of, imagine that if this highest height is greater than smaller h, then there's no height that, like, before you get to that maximum height, you no longer can push the box. Whereas if this big H is bigger, I mean small h is bigger than the capital H, then there's certain height at which you can push it to make it top over. I think that kind of addresses my concern about that the small h, the total height, should somehow be connected to the stability of the whole thing. All right, 6 minutes. So let me type in the answer here. Max height h is W divided by 2 times mu, or 0.8. So it's gonna be W divided by 2 times 1.6, 2 times 0.8. So yeah, and it has correct units. Yeah. C, attach the work. All right, C. And all right, I gotta go faster with the C. Let me just long wooden plank, pin joint, rope attached, hose plank horizontal as shown in the figure. Rope makes 45 degrees. Find the amount of tension in the rope. Okay. So since I only need a tension, let me choose the right center of rotation, so I don't have to deal with, for example, the joint force. So distance h, yeah. So there's gonna be some distance L over 2. That's where the weight of the plank is acting, basically. There's gravity mg at this distance, and there's some distance s. At that distance is where there's a tension force T acting at angle, this angle should be 45 degrees. And I think that's all the forces that I need to care about. Now, there is some sort of pivot force. And as long as we choose this as our center of rotation, we don't have to worry about the pivot force, because all we are looking for is tension force. And we can get one equation that involves a tension force this way. We can write the equation for the net torque, which is going to be, let's say, clockwise is positive and counterclockwise is negative. Then my net torque is going to be L over 2 lever arm times mg minus the lever arm here. Let's do it this way. Let's do distance times the perpendicular component of the force, T perpendicular. So it'll be S times T perpendicular. And pivot force, because the lever arm is 0 here, provides 0 torque. This is all the contributions to the net torque. That should equal 0. So this is a single equation, single unknown. We should be able to solve it. Before we go, the perpendicular component from this geometry should be T times opposite of sine 45 degrees. So it should be T sine 45 degrees, which will be T divided by root 2. So I'm going to be plugging that in here, solve for T. Doing that in the interest of time, let me just do that in my head. T is going to be equal to root 2 over 2 times L over S times mg. Yeah, I think that's right. So that's my T. T is equal to root 2 over, so I guess I can actually simplify this a little bit by de-rationalizing it, which is, I mean, I think the whole process of rationalization, it's the process that made sense before there were calculators. Like with the calculators, I think 1 over root 2 is simpler than root 2 over 2. So 1 over square root of 2 times L divided by S times M times G. Yeah, that's it. And if we needed a pivot force, then we would write the net force now is equal to 0 and use our knowledge of tension force. That's what you would do if you needed a pivot force, or if somehow the question wanted us to deal with this portion, then we would use the pivot force. But as long as we don't need that, this judicious choice of center rotation helps simplify the solution. Okay, 2 minutes. In sports, you may have heard of this using diagrams. So we can use B as an example. If H is greater than the capital H, then the object could be H and let's say and larger H is associated with a higher center of a mass. Then the object could be tipped over by a large enough applied force F at high enough height H. However, if H less than H and smaller H is associated with a smaller lower center of mass, then the object could not be tipped over at all by a horizontal applied force F. And there are other examples too. I think in model answer I give a different example, but this would be sufficient enough. So, so yeah, let me submit this. And or do I have enough time to attach work before I get kicked out? 35 seconds. So I think when I get kicked out, it won't. It'll still save the work that I've had so far. So let me just start attaching work, and I won't worry about getting kicked out. If I get kicked out, it'll still let me continue to edit this box I'm currently editing. So. And I do recommend that when you do this, you take some time to organize your work. Don't do what I'm doing, don't do what I do what I preach. Organize your work and attach your organized work as the attached work. So let me just make sure I bring that. Alright, so I think I attached everything. Yeah, so that's it. Let me submit this. The score will be 0 because it's all manually graded. But after the due date, you should be able to see the answer key icon and double check the answer key and make sure you can grade yourself if you wish. So yeah, that's this additional demo. There was another demo of a static equilibrium situation before, but this is a different version. Because this question is written in a way where the version gets dynamically generated. So this is a different version that I thought would be beneficial for people to see. So here, let me start by identifying all the forces. So as you are applying this force F, the one force that's a given, what you want to analyze this as a quasi-static equilibrium. So you are considering the moment just before when force F is large enough to cause it to start to move. So the moment before that, it's at static equilibrium. So that's how, even though I'm trying to describe something that's moving, I'll treat this like a static equilibrium. So I have this applied force, and I'm gonna have gravity to deal with. Let's say gravity is acting at the center of mass, mg. Now, when you look at these two forces, the net force doesn't appear to be 0, so there must be one more force that causes net force to be equal to 0. That's going to be force that acts on this point. Let me call that F, actually, let me call that normal force because it is a form of normal force. And it kind of has, there's that normal force. And I guess actually there's two normal forces. So let me actually call this N2. So I'm imagining the case where the applied force is 0. If your applied force is 0, then there might be another normal force that's coming from this bottom point of contact. Now, this is what I want you to imagine. As you apply this force, the moment before the wheel goes over, what would happen with this bottom normal force? It would go to 0 because it's about to lose contact. So for the situation that we are interested in, this particular normal force will go away. And we will still have this normal force remaining, hopefully in the correct magnitude and direction to make the net force zero. And so I guess with all that, what I'm trying to say is that this force is going to ensure that net force is equal to zero. If we were asked about this force, we might use this condition to look for what it is. But for the rest of this question, I'm really just going to focus on the net torque is equal to zero condition, because that's the condition that will relate to these two forces. So I hope all this question sets you up for setting the axis of rotation at the point that I'm going to set it at. I'm going to set it at this point of contact. This simplifies my problem because basically it separates whatever force N2 is from the net torque that it'll be, from the torque that it'll be generating. It generates zero torque, whatever it is. So I only have to about torque to the applied force. That's going to be this lever arm. Let me call that R1 times the force F. And that clockwise torque should be balanced out by torque to weight, which will be this lever arm. Let me call that R2 times the weight, which will be generating counterclockwise torque. So that's the equation. R1 times F is equal to R2 times mg. And really the heavy work here is figuring out R1 and R2. So let me draw a nice big figure to try to figure that out. So here's the part of the wheel, and well, this is my R. Let me draw the radius R in two different places. So here's the step size H, and that's the point of contact. So so yeah, the lever arm for gravity, that's going to be, that's going to be easy. So that's this distance, that's R minus H. That's my R1, lever arm for gravity. I know what takes more work. It's the lever arm for, lever arm for gravity. This R1 is the lever arm for the applied force. And that's easy because with these vertical distances, I have R minus H giving me R1. That's the lever arm for applied force F. I'm done. Lever arm for gravity takes a little more work because I need to figure out this distance, which is going to be, I think I need to draw this right triangle. So it's going to be this leg here, and that's going to be that leg of right triangle, which has one leg as R minus H, and hypotenuse as R. So this side should be, let me call that X. So X squared plus R minus H squared is equal to R squared. And when you work out this algebra, it's simpler than I might be afraid that it is. So it's X squared plus, let me expand this out, R squared minus 2R H plus H squared is equal to R squared. So you see that R squareds cancel out, and you can get a reasonably simple expression for X, which is square root of 2RH minus H squared. So that's the lever arm for gravity, or R2. So solving for F here, you get F is equal to mg, that's kind of constant thing in all the answers, times, and this is the ratio, square root of 2RH minus H squared over R minus H. And I think if you factor out one factor of H, then you can, so this is square root of this thing squared.
You can cancel out one factor of r minus h, so you get mg times square root of, wait, is that it? It's possible I made a mistake in this solution, because I think if you factor out one factor of h, it's h times 2r minus h. I don't think that can be canceled out the way it's, I did a cancellation. Yeah, so anyways, so I think the correct answer is just gonna be h times 2r minus h divided by r minus h squared. And the whole thing square rooted if you want. But it won't simplify the way I wanted it to. So, but this is a kind of static equilibrium analysis question that I want you to be able to do correctly. Because I'm pretty sure in the process of writing a solution, I did write it all up, and the r perpendicular is r squared minus r minus h squared. Yeah, okay, I made an algebra mistake at this last step. And didn't realize that no one pointed it out. Okay, but yeah, so you should be able to go through the calculation. I think what I do want to spend, not skip over, is making sure that this setup makes sense. That this is a rigid body with some distribution of mass, and it tells you where the center of mass is. It's being made to rotate about this fixed point. So as we describe torque and other rotation, we are going to use this fixed point as our center of rotation. And we are given this displacement L. We are given height of the most of the mass. And that I want you to have a mental image as we go over this question, so that it's not just the manipulation of formulas, that what we are writing down relates to this physical setup that you have a mental image of in your mind. So let me skip to part C. Is what was too much to test on your exam 2 because of how much topic your exam 2 was already covering. So you are, although probably not as complicated as this exact setup, but you will still be asked to calculate some rotational inertia of a thing that has non-uniform density. And that's a key thing. If it's a body with a uniform density, then you have a table of rotational inertia. You might even be able to use parallel axis theorem to calculate the new rotational inertia about a new axis, so without using any integrals. But to prevent you from doing that, I'll be giving you a question that explicitly has a body that has a non-uniform density. And it's going to be a one-dimensional problem, so you won't have to do any integral more complicated than what you will see here. But so that's the whole setup, that you will have to be able to set up the integrand for the thing you'll be integrating, and you'll have to be able to do the integral. So yeah, read the question. And so this is what the setup looks like. So that's the center of rotation. I guess let me start out with the center of mass of the pirate ship. And this is the kind of representation of the kind of physical extent of the pirate ship. And in the problem statement in the previous page, this was given as L. And this is where you have to read the problem very carefully, because the problem statement defines all these symbols, well, in particular x, it does define h, but h is not defined any differently from how we are using it from initial problem statement, so we can just leave that alone. It's the x where you want to be careful in how you treat it. It tells you how it's treating x. X represents the position on the rod from the bottom of the rod. So the rod distances that x equals 0. So from the bottom of the rod, so it's this position here that represents x equals 0. And I guess the way I have this drawn, x is getting positive, going to the left. So at this position where x is equal to h is where the density of the thing is going to be 0, I guess. So that's the setup. Make sure you spend enough time to have an intuitive understanding of this geometric setup. Then these are the steps that you go through in order to do the calculation of rotational inertia by direct integration. And I don't think I've ever given these as numbered steps. And I hope some of this you kind of think through it and figure it out on your own. And the steps you figured out kind of match to the steps I'm giving you here. But this is one version of the steps that I would give. Okay, so step number 1 is you draw the picture and you make sure that you understand the setup of your geometric object. So let me just call that understand setup. And that's what I have done. And you need to do that so that you can do the second step is you draw a representative mass element. Because what I'm going to need to be able to do is I'm going to need to be able to break this up into small pieces that are small enough that each one of these pieces I can treat it as a point mass. So this is a representative element that has some infinitesimal size. Let me erase this other marking here, which has this infinitesimal size dx, and I'm going to treat this element as having infinitesimal mass dm. And this dm is I'm gonna have to be able to represent this in terms of the density of the thing and the coordinate variable, so that it's something that I can integrate over later. So I have this representative mass element. Okay, so I have that element that I can visualize, imagine for the third step. Third step is write an expression for the infinitesimal contribution to rotational inertia, or what I'm going to label as di. So this is that's the infinitesimal contribution to the rotational inertia, to the whole thing, or the whole rotational inertia of the whole thing, from this small element dm. So it's going to, so remember the rotational inertia of a point mass is mass of the thing times the distance squared, distance from the rotational axis squared. So I'm going to have to write something similar here. I'm going to have to write the mass of this element, that's my dm, which I'm going to expand out a little bit later. And I need to write down an expression for distance here. And in some setups, you can use the single variable to pull double duty, to serve as the coordinate variable and distance. Here, I can't really do that because the problem already gave a meaning for x, and this x does not stand for distance from the where it's being rotated from. So I need to write a new expression that's going to represent the distance, as a function of x, the coordinate variable, so that I can eventually write out everything on the right-hand side in terms of x. So let me just write down this symbolic representation for now. Distance from the rotational axis squared. So that's my infinitesimal contribution. Then I have to rewrite everything in terms of coordinate variable, technically coordinate variables, but I'll only give you one-dimensional problem, so there will be only one variable for you to worry about, and constant. This is preparation for the final step, which is do the integral. Integral over the whole rigid body. So I haven't given you this specific set of steps because, you know, at some point the problem solving, it's not following a rigid set of steps. We did that with a standard strategy as a kind of model of coming up with a problem solving strategy. But as you continue your study of physics and engineering, you should develop ability for yourself to come up with these strategies on your own without someone giving this to you, well, without someone spoon feeding this to you. So here I have two expressions that need to be expressed in terms of a coordinate variable, dm, and the distance d. The dm is the easier one. That you kind of get it from the definition of density. So density is that's the length per, that's the mass per length. So really what the density in a kind of rough schematic symbolic term, it's the, well, amount of mass per length. So you can rewrite this, there's a bit of an abuse of notation going on, but ignoring that, you can rewrite this to get an expression for dm. That's the density times dx. So I'm going to be writing this with the density as a function of x. It's already given to me as a function of x times dx, and that'll give me the mass element in terms of the coordinate variables that I'm looking for. The part where you need to spend a little bit of time thinking through is the distance from the axis of rotation. So because you need to kind of think through this geometry here. So it would have been easier if somehow the L that we were given wasn't overlapping with the H at all, but unfortunately they overlap. So so I think I need to start up by figuring out how much this overlapping portion is. And I have a feeling, here it is. Hint, the center of the mass of the rod is at h/4 above the bottom of the rod. Okay, so I guess what I'm given actually is the portion that is not overlapping. So instead of the portion that's overlapping, I'm told the portion, so if this is where L ends, L is to the center of mass. That's how it was described in the previous page. Then this distance here, I'm told in the hint, is h/4. So these are some a few points where you can check check the expression that I'm going to be writing down. That d at x equals 0, that has to be the entire distance L plus this portion that's not overlapping. So that should be L plus h/4. That's at d of x equal to 0. And just to have more confidence with the expression that I'll eventually write down, I can write down a fixed expression for D where x is equal to h. That's at the other end of the pirate ship, and that should be L minus this overlapping portion, which will be the h minus h over 4. So it should be L minus 3/4 of h. So this is why I take pains to draw this figure, look at this figure, make sure that the expressions that I have here fits in with the geometry that's represented in the figure there. Take a minute or so verifying that. Once you are sure that these expressions as something that represents the value of D at this fixed point, then now your job is to try to come up with an expression for D. And after some trial and error, this is what you should come up with. D of x is equal to this maximum value, L plus h over 4 minus x. And you can double check that by plugging in, I guess, x equals h, and looking at how the d varies as x varies. And so once you are confident with that, then now you're ready to write down an expression that you can integrate. The infinitesimal contribution to the rotation inertia from this tiny section of the pirate ship is, it's gonna be integrated with respect to variable x times, let me write down L of x, that's 3m over h cubed times h minus x squared, that's the density, times this expression here, d of x, L plus h over 4 minus x squared. So you have to integrate this over the entire rod to get the rotational, entire pirate ship. So entire ship to get the rotational inertia of the ship. Then what that
question?
Yeah, question.
Yeah, the question is like, how did you get the x when you solve for the d all x as a function of x, L plus h by 4 minus x? That's what the confusion.
Trial and error. Let me just so I say trial and error because there is no one single fixed set of steps I can give you that'll work all the time. This is really the intuitive portion of this problem solving. I think what I can guide everyone to is writing down this expression that at x equals 0, that this is the correct distance. Yes? And also yes.
Yeah.
And
Okay.
that this is the correct expression for the other end of the pirate ship, that at this end, that this gives the correct distance.
Right.
Those fixed points, they are easier. Those are the ones you can come up with relatively easily. You just draw the picture. And writing down this d of x as a function of x, that is the hard part. So what you do have to guide you is that from the problem statement, x was defined to be 0 here. And that x increases going to the left, increasing up to h here. So at this point, really, what I would say is trial and error. So you know that whatever you come up with here, it's not going to go like x squared, and it's not going to go as 1 over x. It's going to be something that's a linear function of x. Right? There's no other choice that would make reasonable sense. Then you might try something that looks like a d of x is some constant plus x. Then as you try that, you should figure out fairly soon that, oh, that makes no sense. It's not going to fit with these two facts that we are trying to fit this to. So once you make fail at that plus sign making it that work, then you try to fit d of x is some constant minus x, and hopefully there's enough intuition that you realize that there's no coefficient in front of it. Like it's not going to be minus 2x or minus 3x. It's how the distance changes. It's going to be just it's going to be same scale as how x changes. And so at this point, so once you figure out this much, that the portion that depends on the variable x is minus x, then the rest is really figuring out this portion by trial and error. You want this to be correct so that when x is equal to 0, that you get this value. Then, that makes actually L plus H over 4 a fairly pretty good guess to try here. L plus H over 4. Now, if that's all you did, then you have no confidence whether this is correct or not. You're just guessing. When you are doing things by trial and error, you need some way to check your guess. That's why I have this second expression here, so that I can plug in, a value of x equal to h, and see if I get a value that I thought I should get when x is equal to h. And when you plug it in, you get it.
Okay,
So
I understand. Yeah, I think I understand.
Yeah, so this is really why there's no substitute to practicing physics problems, because some of the solution steps, there's no specific instruction I can give you. The only instruction I can give you is trial and error. And the best bet for you for this trial and error process to take place is really in the comfort of your own home with a practically unlimited amount of time, not in the context of an exam setting where you only have 2 hours, and if the first 2 or 3 things you tried didn't work, then you are practically, well, you're done for the exam. So this is why practice matters, because some of the problem solving, it really only comes through by trial and error. And you need plenty of time to try that trial and error. So for the rest of this problem, I'm going to take this as given, that you came up with this through trial and error on your own time somehow, and that you double checked it with the expression with the constant checkpoints that you thought should work. So we were at trying to do the integral for the ship. And I start out with this kind of schematic description of integral over the ship. And the task for you is then to figure out what are the limits of actual integration that corresponds to this schematic or kind of descriptive representation of the object that you're integrating over. So when you're integrating over the ship, you're starting from here, x equal to 0. And you are ending at this point at x equals h. So you integrate from x equals 0 to h, and that should work. And I guess I won't actually do the actual integral other than I can show that it's doable. So let me do that with Wolfram Alpha. This was one of the kind of thing I regretted writing out the exam solution 2 years ago, that this was too long. That all these polynomial expressions, it's doable, it's polynomial integral, everyone can do it, but it takes quite a bit of work to work it out. So if I were to, I know that now, so I'll be mindful of how long that particular complex of a polynomial integration takes. But let me just do this on Wolfram Alpha just to show that it's doable. Integrate, so 3 times m divided by h cubed times h minus x squared times L plus h over 4 minus x squared. I'll probably get rid of at least one of those squares if I were to give a similar problem. From x equal to 0 to h. And Wolfram alpha is usually good about interpreting what I mean. So it did interpret correctly. I mean to integrate with respect to x and verify all the rest of the mathematical expressions are fine. Then after you're done with this complicated integral, indefinite integral, you end up with this definite integral, which hopefully matches the solution that I posted. So really, and this is the thing that I'll be trying to test for. Given a new situation that involves variable density, so that I know you have no other way to solve it other than to set up the direct integration and actually do the integration. Are you able to understand the setup that's described in English words mostly? And are you able to isolate kind of a representative mass element which you can use to write out this infinitesimal rotational inertia? And can you go to the step of rewriting this portion here in terms of the coordinate variable in preparation for doing the integral? So that's what I'll be looking for. So this is the kind of representation of direct calculation of rotational inertia by direct integration, and yeah. So and I think it is important for you to develop the skill to for coming up with the expression like this. Frankly, a lot of the things you might do for a physics exam, it's a step that can be automated. You saw me do the integral on Wolfram alpha in 1 second. It's like, so your skill in evaluating this integral by hand, it's not a valuable skill. You can, computer algebra system can do that a lot better and quicker than you can. But the skill that is valuable in an engineer or scientist is the skill to come up with this expression. That's the one step that can't be automated, that requires a human being with an intuitive problem solving to write down. So I'll try to test for that somewhere in your exam. So I guess, should I? Well, let me just give you the answer to part A so that you can, if you're answering it for yourself, you can at least check your answer. So I have this ballistic pendulum being described. This is a reached rod. So it says that this mass will come in, strike, and then it says become stuck to it. And that's a key phrase because becoming stuck to it, it describes a completely inelastic collision. So when you are answering part A, for total mechanical energy, you should say it's not conserved because the collision that you are seeing as it's described is a completely inelastic collision. And when you look at the total linear momentum, this should be conserved. And total angular momentum, it's also conserved. And both of them are conserved for same or similar reason. Total linear momentum is conserved because net external force is equal to 0. When you look at this collision process through the free body diagram of these two masses, by the way, I'm going to say gravity is negligible. Because I'm kind of looking at the short duration and the impact force will be much greater than gravity. So I'm going to say gravity is negligible. That also make this tension force negligible. So really the only two forces you have are force of interaction between these two masses. Oops, they should have been the same length because these are action-reaction force pairs, so they will have an equal magnitude, opposite directions. So that external force is 0. Yeah, I think depending on how it's set up, there's a chance for some pivot force to be involved there. I think the way it's set up here, the pivot force should not come into play. Uh, and that would be a complication that you wouldn't have to worry about. And the total angular momentum, it's also conserved because net external torque is equal to 0. The only forces that could have been applying torque here would be either some sort of frictional force that's involved at the pivot. And I think, do I say frictionless pivot? I don't say frictionless, but we're going to assume it's frictionless. And so total angular momentum is conserved. So those should be answers to part A, once again, which covers topics that we don't really cover for our exam 3. So the material that's more relevant for our exam 3 is what I'm asking in B and C and D, which is basically asking you to remember what you remember about oscillations. So it's saying that, let me just draw the picture here so that I don't have to keep moving back and forth. So after collision, what you basically have is a combined mass of m plus m that has some initial velocity v naught. And it's saying assume that this is small enough that the subsequent motion can be approximated as a simple harmonic oscillator motion. And it's actually saying two things. One, it's saying that this is small enough that this is not going to go all the way around. Like if you did that, then it wouldn't even be simple pendulum. It's saying that this is small enough that this is going to swing back and forth like a pendulum motion. And it's actually saying a second thing about how it can be approximated as a simple harmonic oscillator motion. If you remember the thing about pendulum being an example of something that's not necessarily a simple harmonic oscillator, it's also saying that this amplitude, so when it gets to the maximum displacement, that this angle is going to be small enough that we can treat this as, we can use a small angle approximation and treat this as simple harmonic oscillator. So it says calculate in terms of given quantities in symbols, angular frequency of oscillation, and amplitude of oscillation. Well, angular frequency, you're not actually calculating that, you're just recalling, memorize the formula, which is angular frequency of a pendulum is given by square root of gravitational acceleration g divided by L. So that's it. You remember the formula or have the formula written down in your formula card and write it down. That's kind of all that you need. You do need to calculate amplitude of oscillation. And for that, the thing to do would be to use conservation of energy. So you are given this position here where you are starting out with initial angle v naught and initial speed v naught, and you want to describe the highest point here, which will be giving you the amplitude of oscillation, theta max. And one principle you can use to take you from this snapshot 1 to snapshot 2 is conservation of energy. So you say whatever kinetic energy you have at this point goes into the potential energy at point 2. So let me write that down. So this is the total energy at snapshot 1. So kinetic energy at point 1 plus potential energy at point 1 is equal to snapshot for point 2. And as a matter of good practice, good habit, let me just write down all the terms. Kinetic energy at point 2 plus potential energy at point 2. So kinetic energy at point 2 is going to be 0. That's the maximum height. That's where velocity is equal to 0. Now, potential energy at point 1, we can always do this. We can say this represents my y equal to 0. So this put a position where the distance of the mass from the pivot point is L. I'm going to call that my 0 point. That reference point will make expression for my potential energy equal to 0 at that point. So what I have is then a way to say, all right, my kinetic energy down at that point, 1/2 mass times the initial velocity squared is equal to potential energy at point 2. And what I need to figure out is this difference in height. And let me draw a new figure for that. So let's see, here's my L. Now at that maximum height, this distance is still L, it's the same rod. So this is the right triangle that I have to draw. So this is my theta max, and this difference in height, what it's going to be is, let me, I don't know, let me just use capital X. This difference in height is going to be L minus what I'm labeling as capital X here. This side of the triangle minus capital X. So from this right triangle, you see that capital X is L cosine theta. So put that in here. L minus L cosine theta, or L times 1 minus cosine theta. So putting that into the expression for gravitational potential energy on the right-hand side, it's going to be mass times G times the change in height, which will be L times 1 minus cosine. And this theta is the theta max, or the amplitude of oscillation. And the rest of this question is going through this algebra and solving it for theta max. You see some things simplify, and you might in the end write down theta max in terms of arc cosine of some quantity that you're going to work out algebraically. That's a fine answer. That's fine. There's another way to answer this. Especially if you feel comfortable with small angle approximation. So since we are using this small angle approximation anyway, you could say, all right, so let's say I can use small angle approximation to rewrite this cosine of theta max. Now, what you do have to be careful with is, so if you say this is approximately equal to 1, you'll get 0, and you won't get an expression that involves theta max. So what you have to be careful with is you have to be careful to go the next step in the small angle approximation. And that's why I'm saying you should feel comfortable with this. The next term in the Taylor expansion is minus theta squared divided by 2 factorial. So so I can approximate this cosine of theta max as 1 minus theta max squared over 2. You see the ones cancel out, minus cancels out minus, and I get this parenthesis term to be just the theta max squared over 2. And that's where you can relate theta max directly to all the other terms, just algebraically, without having to go through a trig function. Either approach is fine. I think at this point in this class, you are not expected to be super familiar with the Taylor expansion. So if you'd rather do this exact expression for theta max, which isn't wrong, then that's fine. I guess that's better than using just the leading term and then not getting an answer. So that's why I present this first. But for those advanced people who have taken Math 3B and feel some level of familiarity with Taylor polynomial, then this is the approach that I would encourage you to consider. So that you get an expression for amplitude of oscillation that you can relate to other quantities like angular frequency of oscillation and all that good stuff. Okay, continuing, part C. It's asking what is the angle theta. And let me just expand this a little bit. All right, I'm gonna.
This is why I usually preload the dice before the meeting, because this can take. Okay, I haven't done this question before, so I will do that. Okay. So, this question says, a uniform rod of mass, some mass, and some length is free to rotate. Okay, the rod is released from rest. And, oh, they've given the angle. Okay. For each question below, keep an organized record of, okay. What is the angular rod? So let me just sketch this out so that I have a way to think this through. So I have a rod, and after this swings down, the rod is going to be at through the horizontal position. So I'm looking at when the rod is going to be at this position, swinging down. So I'm thinking through two snapshots, snapshot A and B, and when it asks angular speed of the rod, I'm thinking through well, so by this time in the class, we've covered quite a few, well, 3 or 4 problem solving strategies, tools. Of those, the one that I always recommend that you try first is conservation law. Not because it'll always work, but because when it doesn't work, it'll be relatively quick to rule out. So you have to think through what kind of quantities are conserved, and if there's no conserved quantity, then okay, you can use it. Here, I have a sense that with all the description I have so far, that this is free to rotate, and I don't get the sense that there's any non-conservative force doing work. So I think energy will be conserved. So we'll work with the conservation of energy and see if it gives us enough information to write down enough equations to work out what it's asking for. So they are asking for angular speed. Yeah. So what is the angular speed in snapshot B? So I start with my conservation law equation, which is to say the total quantity of the conserved quantity, total energy, in one snapshot is equal to the total energy in another snapshot. That's what it means for energy to be conserved. And I write out all the different contributions to total energy that I can have. I have gravitational potential energy. I have potentially kinetic energy, but I can get the sense that I think it's released from rest. Rod is released from rest. So I'm gonna say, okay, the kinetic energy here will be 0. So I won't bother writing down all the things. And I'm going to have gravitational potential energy of the rod at snapshot B. Let me do this thing that makes things simpler for me. Let me say y is equal to 0 here. Then I can write down my gravitational potential energy at that point is going to be 0. So now I have to write down the different forms of kinetic energy. It's going to be 1/2 mass of the rod times the velocity of center of mass squared plus 1/2 I omega squared. Now here I think I actually have 2 different choices. So the version I've written is where I write down translational kinetic energy of center of mass and rotational kinetic energy about center of mass. This is something that you can always do. You're never forbidden from doing that. Now, in this setup, there's one simplifying feature. You have a fixed point. So you could choose to describe the entire thing as just the total rotational kinetic energy about the fixed point. So you could write down just 1/2 I omega squared. The main thing to be careful is that your omega should be the correct expression for the rotational inertia, rod spun about one of the endpoints. Now, since that's a little bit of an easier method, let me do the harder one just to show. So, you can do the easier one and use that to check my answer. Make sure that they agree. Both methods should give you the same answer if they are both correct. So let me write this out. The gravitational potential energy, I have to be careful. I have to use the center of mass to express the gravitational potential energy. Let me write this as a lowercase h for now, and I'll write it in terms of given quantities later. I think, yeah, length L. So, well, when I do later, it'll end up being L over 2 for half of the length times sine theta. That's what that height will be. So gravitational potential energy is mgh is equal to that expression, 1/2 mass times the velocity of center of mass. Let me write it that way for now, and I will have to rewrite it in a bit. Plus 1/2 the rotational inertia of a rod spun about its center of mass. You should know where to look it up from, from our textbook. Know what section to go to. Here, in the interest of time, I'm going to write down the expression that I do have memorized. This is a 1/12 mass times the length squared and omega squared. Now, as you look at this expression, before you start doing any algebra, you should always do this step. Count the number of equations, one equation, and number of unknowns. So, mass is known, or you treat it as known, hoping it'll cancel out. G is known. H, I have an expression there, so let's say it's known. And you have velocity and omega. You have two unknowns. So one equation, two unknowns, that's actually not enough to solve. So here you have to think through and get an expression for velocity of the center of mass, how fast this point is moving in terms of angular velocity. And if you have this is the expression that comes up in like rolling without friction, rolling without slipping and other scenarios. You should have this relationship between tangential velocity and angular velocity. The tangential velocity at this point is equal to the angular velocity of the whole rigid thing times the distance to the fixed point. So that'll be L over 2. So I'm gonna plug this in, make this into equation of only one unknown in terms of all known quantities, and I'll plug in the expression for H as well at the same time. So mg L over 2 times sine theta is equal to 1/2 m L over 2 squared omega squared plus 1/2 1/12 ml squared. Let's scroll a little bit. Omega squared. I hope you see that omega squared and like factors out. So I can do a little, or ml squared can factors out. So let me do this simplification. mgl sine theta over 2 is equal to, let me factor out the things that factor out, ml squared omega squared, and the rest is a matter of the fraction algebra. So 1/2 times 1/4, so 1/8 plus 1/2 times 1/12, so 1 over 24. And I can do a little bit of cancellation for simplification. Mass cancels out, one factor of L cancels out, and I think I can solve for omega. In the interest of time, I'll leave fractions as they are. That's perfectly allowed to do. So doing the rest of the calculation in my head, omega is square root of g sine theta over 2L, don't forget that, times 1 over 8 plus 1 over 24 square rooted. So that's my answer for A. I think I already used the 10 minutes. Sine theta divided by 2 times L times 1 over 8 plus 1 over 24. That's omega is equal to that. Yeah, 10 minutes. Okay. At the moment when the rod is in the horizontal position, what is the angular acceleration of the rod? It's actually an entirely different question. So when you are doing this question, so you would think through, okay, can I answer this question using conservation law? And your answer should pretty quickly get to, oh no, I can't. Conservation law doesn't give me angular acceleration, and while there might be a way to get at it, it's going to be really complicated. So at this point in the step, you should try other problem-solving tools you've learned. And one of the tools that you have learned is the standard strategy, Newton's law. Newton's law gives you acceleration with the translational motion. So you use the rotational version of that. So I have this extended body. I have the pivot point. And I can say that all the gravitational force acts at the center of mass, Fg, and there's going to be some sort of pivot point that I may need to figure out. And let me look at it here. So I'm only looking for angular acceleration. Angular acceleration is net torque divided by rotational inertia. If I treat this motion as being pure rotation about this point, that'll simplify my calculation a lot. I don't have to worry about torque due to the pivot point because the lever arm is 0. This lever arm is super simple, L over 2. So I can just write out the rest. My angular acceleration is going to be net torque, which is due to just this one force. Clockwise torque due to gravitational force, mg. The lever arm is L over 2, so L over 2 times mg, that's the net torque, clockwise, divided by rotational inertia. And here you have to be careful, because I'm using this as my center of rotation. I should make sure that I use the correct expression for rotational inertia of a rod spun about its end point. So it's going to be 1/3 ml squared. And even though you don't have to have this memorized, you can look it up in the textbook. Having it memorized will speed up your problem solving. So I do recommend having it memorized. Sometimes, if you work with these enough, they kind of automatically get memorized. With the practice comes like that. So, okay, so it's going to be 3/2. 3g over half L. So that's angular acceleration. Alpha is equal to 3 times g over 2 times L. All right, I got how many time? 7 minutes. Okay, for the remaining 2 questions below, assume that and that. Okay, rod swings down. Consider the moment when the keeps changing positions. All right, rod is gonna be now in the vertical position at the bottom, I think. Okay, let me call this a snapshot C. I estimate the force on the rod at the pivot point at this moment. Oh, I see. So I can think through 2 things. So, so because it's asking you for the pivot force, here now you have no way of avoiding doing the standard strategy and actually figuring out what the pivot force will be. Now, as you draw the free body diagram, if you are thinking that on this extended object, I have a force of the pivot here, I have gravity acting here, and you are thinking, oh, they are gonna equal and opposite. So net force Fp minus Fg will be 0. If you do that, you have fallen into my trap of trying to get you to say that pivot force is mg. What you have to consider is you have to consider the fact that this is moving. It's got some speed of the center of mass. And now, to do this correctly, you have to actually treat this as extended body and do all that. But on order of magnitude estimate is fine, and I think I have only like 5 minutes left, so I'm gonna just treat this, do this alternate picture, one that makes a calculation doable, one where so I have the pivot force that I'm considering, and I'm going to treat all of my mass as if it's at the center of mass, moving at speed v cm at that point. And let me just make sure my velocity vector is not mistaken for force vector. And there's going to be gravitational force mg pulling it down. So when I calculate the net force, it's not going to be a 0. It's going to have centripetal force to keep this mass in circular motion. So it'll be mass times v cm squared over the radius, which would be L over 2, L over 2. So that's what I have to work out. So I see that I have one piece of missing information that I need to work through, my VCM. I can't just reuse the VCM from above, although I can reuse many of the pieces in the calculation. I just have to use the apply the conservation law strategy again in the context with the snapshot C. So let me just paste that over here and make the necessary changes. So my snapshot B is now changing for snapshot C. Let me erase this. And I'll still use the same, actually, so can I? Or I think I'm running out of time, so let me, in the interest of time, let me do this. What I can do is, instead of redoing the whole wait, no, I do have to redo the whole calculation, never mind. I thought I could take the result in A and double it, but I don't think I can, because the geometry that I'm ending at, it's not symmetric, so I actually have to work out the whole thing. So so I have this. So snapshot A doesn't have to change. I'm gonna keep everything on the left hand side. All I have to change are the things on the right hand side. This will be C. Let me just double check the time here. 3 minutes. Okay, might be enough to work out part C. So here, all of this expression doesn't change. What is changing? Oh, I see. I said gravitational potential energy is 0. It's not gonna be 0. It's gonna be minus mg times L over 2. So I have to put that in. So wherever I see L over 2 sine theta, that actually is going to become that's gonna need plus L over 2. So I guess what that means is sine theta gets replaced by sine theta plus 1. Yeah, so sine theta plus 1. So that's gonna be omega. So so my V center of mass will be L over 2 times this omega. So let me just type this out. The F pivot is equal to m times g plus m times v center of mass squared over L over 2, where v center of mass is equal to L over 2 times omega, where omega is equal to square root of g times sine theta plus 1 divided by 2 times. I'll double check this answer with more time when I have more time after the time limit runs out. And this is a complete answer because I've given this expression in terms of all the quantities that I can actually get numerical value of. And I'll say I'll plug in numbers later, running out of time. So I'll do D first. Estimate the amount of time necessary for the ride. Come back to the original position. That's so. Oh. So easiest way to do it is to get the VCM here, or running out of time. How I would do this is I will get a VCM from above, take VCM over 2 to be approximately the average speed, and then actually get omega from above, take omega over 2 to be approximately the average angular speed, and then take the total angular distance of so it's going from 60 degrees down to 90, and then so it's going to be 180 plus 280 degrees, so pi plus 120 is so that's gonna 120 is what I think 2/3 pi. So that's gonna be 5/3 pi. Take the distance that and divide it by the average angular speed, which will give an approximate amount of time. All right. So let me wrap this up in the yeah. So I'm gonna just do this thing in Sage Math. So actually, let me use the online version of Sage Math, and yeah. So this will, I think, work well enough. So Sage cell, I think, I don't remember URL. Okay, so we'll declare the variables. So I just using this to plug in numbers. I need velocity of center of mass, or swing down. Yeah. So my expression for the F pivot, FP is well, actually I don't need that. M G M V C M L. So my expression for F pivot is M times G plus M times VCM squared divided by L over 2. Oh, I have to print FP. It'll show me that expression. Great. I need to plug in the numbers. I need the expression for VCM actually. So let me do this. I'm gonna FP substitute in for VCM. That's gonna be what I have there. L divided by 2 times omega. Oh, I need the expression for omega. And after this, I'm going to substitute in what omega is. Omega is square root of g times the sine of theta plus 1 divided by 2 times L times 1 over 8 plus 1 over 24 square rooted. Okay, I need the symbol for theta. So let's see if that gives me something that's an expression. I incomplete input. Okay, I think I probably was missing. Yeah, missing a incomplete input. Let's see. Oh wait, I need one more parenthesis there. All right. Okay, so I have some expression there. Let's plug in everything. So into that expression, I'm substituting in m is equal to 0.1 kilogram, L is equal to 2.5 meters, and actually, I think I can do a line break. Yeah. And what else do I need? I need theta 60 degrees, which is pi over 30. Let me do numerical approximation over 33. Pi over 3, that's 60 degrees. I need a G of 9.8. I think that's everything. Evaluate. So 3.723, that should be in newtons. So I'll say, okay, so that's gonna be it, and replace that with that. So F pivot is 3.723 newtons, probably. We'll double check with the answer key. So I think the way I was doing it here, I didn't quite get the intermediate number I need. So let me so let's call this FP number, and let's go get the expression for omega. Yeah, so I actually just needed this. Actually, I could have been a lot simpler. Sorry, that was omega, and into that I just want you to substitute in this. Okay, that's what I want. Unmatched. Oh, pretty sure. Yeah, there's a square root thing, so I need the whole thing to be inside that. Okay, so this gives me omega. Let me make sure. For the omega at the bottom is given by. So omega is 4.684 radians per second. So the average omega is half of this. Omega average is 2.342 radians per second, and since average omega is delta theta over delta t. Delta t is delta theta over average omega. And I worked out delta theta in the answers above. It was 5 over 3 pi. That's probably right. Within order of magnitude anyway. So it'll be so 5 over 3 pi divided by 2.342 radians per second is equal to, and I'll just do the calculation in Sage Math since everything's already set up here. So this is going to be omega average if I multiply this by 0.5, and I have, for the delta t, it's going to be numerical approximation of 5 over 3 times pi divided by omega average. So 2.235 seconds. 2.235 seconds. So okay, so let's save work and continue. All right, this is the test the students work. Attempt 4, great. So I had this, g sine theta and all of that. G sine theta, 3 over L. So to be able to compare, I'm gonna need this. Let's see here. So what I need is I need a numerical version of that expression to make sure. So I'm gonna do everything except for square root of g over L, and it should come out to be 1.612. So let's do that. Square root of sine of 60 degrees or pi over 3 divided by 2 times 1 over 8 plus 1 over 24. And numerical version of that. It's 1.61, close enough to 2. Yeah, good. and so that's correct. And the answer here, 3g over 2l. Yep, that's correct. Good. And this is where it gets tricky. So within my attached work, what I worked out was it was going to be 3.723 newtons. Let's see. 3.723 newtons. And in fact, the way I approximately did it is how I would expect people to do it. Now, to do it exactly, you have to... Oh, wait. Yeah, here actually the exact answer matches the approximate answer, but it's pure accident. I don't think they're in general expected to match up. And here I worked out the duration of time of 2.235 seconds, and that was 2.235. The approximate time, where is it? Did I miscalculate? So they work. Oh, I missed because I worked it out for where it gets here. So the number I have, you have to double it for it to be correct. So the number I have here, 2.235, you have to double it for 4.47. So let's see if it's 4.47. Yeah, 4.47. That's the answer. Yeah. So okay, factor of 2 error. And to do it exactly, the answer key does it with this Sage math code. And it's actually pretty close. It's not too far, approximately 3.9. And this is imaginary, I think. 3.915, so it's, you know, within what, 20% of the approximate value. So okay, let me start. And I think this is a question from Portable TA. So back when we used to have midterm exams, one of the promise to my students is, hey, one of the questions is gonna be from Portable TA. Use that to study. Um, so, anyways, so let me work through. And if you want, you can compare my answer with the answer you see in the Portable TA. So okay, it says consider a yo-yo with a very light string wrapped around with some radius there. Okay, yo-yo is approximately a solid disk. That'll be important because that determines what kind of rotational inertia formula I use. And just as a reminder, rotational inertia, I mean, I guess it's open book. So if you're using textbook, great, that's fine. No restrictions there. And in the past, when I didn't used to have open book stuff, I still gave people the this table. So in the moment of inertia section 10.4, there's a table of moment of inertia, and that's the kind of information that I don't really require or expect people to have memorized. I do happen to have memorized some of these just by using them so much. But like a table of formulas like this is something that you should expect to have access to in your normal work, academic, and professional, and that's fine. So solid disk means the rotational inertia will be mass of the disk times r squared divided by 2. Treat the material as negligible, good. Somebody holds the end of the string motionless, good. So I think energy will be conserved. Release from rest. Yo-yo falls and rotates. Okay. For attached work, draw a free body diagram. Okay. So I'm gonna draw a free body diagram of yo-yo as it falls. So so I'll have some representation of the physical extent of the yo-yo. So the outside disk and the inner ridge. So as it falls, I think it'll have only two forces on it. The first is the force that's always there, gravity. I'm going to treat that as acting at the center of mass of the yo-yo. And there's going to be tension force that will be acting where the string attaches to the yo-yo. This will be the tension force. And I think that's it. Briefly describe. Okay. So there are two forces on the yo-yo. The downward force of gravity mg acting at the center of a mass of yo-yo. Geometric, same as a geometric center for uniform disk. And the upward force of tension T acting at the point where the string touches yo-yo. Good. What is the tension in the string as the yo-yo falls down? Express your answer in terms of, okay. So this is a standard strategy question because, well, it's asking us about force. And if it's asking about force, it's a good chance that we'll need to do a force analysis. If you are creative, sometimes there's a way to use other methods like conservation of energy or sometimes even momentum to kind of first work out energy and then work backward. Let me keep it simple, use a standard strategy. So I already drew a free body diagram and I should be defining my axis. And with the rotation, when you're defining axis, you're actually thinking about two things. One is the, regular kind of x, y, and axis. The other thing to consider is because you're going to be calculating torque, you should think about your center of rotation. Here, I think I'm going to keep it simple. This will be my center of rotation. I'll say clockwise is positive, counterclockwise is negative. That's how I'll do it. And I need to break down forces into components. Don't need to here because everything's already along the y direction. So finally, I need to write down my net force equation and net torque equation. So net force, upward and down. So let me call down positive because my acceleration will be downward. So technically I should have labeled the downward as x, but I don't really need to deal with the x and y distinctly, so I'll just uh, wing it. So net force, downward being positive, is gonna be mg minus tension is equal to mass times acceleration. Okay, that's one. Net torque is equal to, I write down all the torque terms. I have the lever arm for the tension. Oh, so I should have this distance labeled. I think in the question, this question that said that was R over 4. This part might be randomly generated. This factor 4, I probably randomized it. So, so that's the lever arm for the tension force, R over 4 times the tension force, plus, now gravitational force might have had a lever arm if I didn't define my center of rotation to be here. That's actually the reason, one of the reasons I defined it there. So gravity provides zero torque. That should equal rotational inertia times angular acceleration. And if I want, I can even put in what rotational inertia is. That's mr squared over 2 for the solid disk times alpha. So this is the end of the standard strategy. And before you start doing any algebra, you should do this check. You should do this check of, are my system of equations solvable? So I have two equations. So it's a question of, do I have only two unknowns or more? And counting, I don't know tension, I don't know acceleration, I don't know angular acceleration, and am I given the mass? Yeah, I guess I'm given the mass. So yeah, that's I have three unknowns, two equations, which means I'm missing some piece of information that I need to actually be able to solve it. And as you think about it, I hope you eventually come across that something called rolling without slipping. And I think the question even gives you some hint to that effect. Somebody holds, or maybe not. So they don't tell you that the string doesn't slide against the yo-yo, but that feels like a natural assumption to make. So I'm going to make that assumption, which means as this yo-yo rolls down, that will be like a rolling without slipping, in the sense that the amount of string that gets pulled out of the yo-yo, there's a correspondence to that, and the angular distance that it rolls down. So all of that to say, I can relate this angular acceleration to this acceleration. Acceleration is going to be that radius of that circle, r over 4, times the angular acceleration. That's my equation 3. So now I have three equations, three unknowns. I should be able to solve it. Since in this question my interest is in the tension, let me do this. I'm going to systematically eliminate alpha and a. That'll hopefully end up with one equation in terms of tension, and I can solve for it. So let me do this. Since I have an expression already solved for acceleration, let's plug this into 1 to eliminate acceleration from my expressions. So this is coming from 1 and 3. You end up with what I'm going to call 1b mg minus t is equal to m times r over 4 alpha. Let me write down equation 2 again for just comparison and kind of thinking through what to do next. The lever arm times the tension force is equal to mr squared over 2 alpha. And be careful with the difference between the lever arm distance here, which is tied to this radius of the inner ridge, where the torque will be generated, with the radius here. So the radius here is the radius of the entire yo-yo, because we are dealing with a solid disk of radius r. That's for the rotational inertia. Make sure none of those confuse you. Okay, so I guess I need to eliminate alpha. So let me do it this way. I'm going to solve the simpler equation for alpha. When I do that, I get alpha is equal to, I'm gonna just do the algebra in my head. Or let me do some cancellation here. R cancels one factor there. This cancels one, well, 2 to get down to 2. So 1 half t is equal to mr alpha. So now solving that, I get t force divided by 2 times mass times r is equal to alpha. And I think I do get the right unit, 1 over second squared. So, yeah, because t is kilogram meter per second squared. So now I can plug in this alpha into equation 1b to get this. So I get equation 1b and equation, I guess this is technically 2b. Then I end up with mg minus t is equal to mr over 4 times t over 2 mr. So I have to collect the like terms. Let me cancel the things that cancel, because actually this m cancels with the dead m. Dead m I think stays there. This r cancels with the dead r. So I have t over 8. Yeah, okay. That which has, okay, so let me write that out. Right hand side is actually equal to t over 8. Okay, then let me collect the like terms. Collecting like terms, I move this minus t over. So on the right hand side, which I'm going to write on the left, I have 1 plus 1 over 8 times t. On the left hand side, which I'm going to write on the right, is equal to mg. Now I can solve for t is equal to mg divided by that, which doing the fraction simplification in my head is 8 over 9. So t is equal to 8 over 9 mg. That feels right, that at least that's the correct unit. And one thing that makes me feel comfortable is if the yo-yo wasn't falling down, t would have equal to mg. Yo-yo is accelerating down, t is slightly less than mg. I think that makes sense to me. So right, so tension in the string is gonna be equal to m times g, g times 8 divided by 9. And the rest is in the attached work. Alright, yeah, so I didn't, oh wait, I didn't need the G, capital M. I didn't need the M, and it should be capital M. So, yeah, I guess, so I don't need the R, huh? Could be surprising. I think it is a factor of 8 over 9, probably depends on the inner region being a quarter R. So, okay, after the yo-yo falls down distance h, how fast is it falling and rotating? Oh, okay, it feels like I actually have to finish solving for alpha and a. So let's do that. So for part C, I'm gonna just continue on with what I was doing in B and actually solve for alpha. I'm a little hesitant to use t to directly to get like the angular velocity and the velocity, because when I calculate work and do it that way, I've made the mistakes in the past. So okay, alpha is equal to, let me just write this out, 8 over 9 times mg divided by 2mr. So some things cancel, masses cancel. 2 cancels a factor of 2 there for 4/9. So that's equal to 4 over 9 g over r. And I think the units are right. And with that being alpha, then so a is equal to the radius r over 4 times the angular acceleration. So let me write that out. R over 4 times angular acceleration 4/9 g over r. Okay, 4's cancel, r's cancel. So I get the acceleration of g over 9. Okay, so how fast is it falling and rotating? So I think let me do it this way. Acceleration is equal to g over 9 and angular acceleration is equal to 4/9 times g over r. Let's see attached work. Since it's a constant acceleration, from kinematics formulas. I think I'm gonna use the v squared formula. I can say v final squared minus v initial squared is equal to 2 times acceleration times the distance h. So I can solve this for vf, and vf is equal to square root of v initial was 0, so I have 2 times the acceleration, g over 9 times the height h. So that should be the final speed. That being the final speed, omega final will be this thing divided by r over 4. So it'll be, well, let me write it this way. 4 over r times square root of 2 times g times g divided by, oh wait, I gotta be careful here. 9 times divided by 9 times h. So I think that's it. Wait, did I miswrite it? Yeah, sorry, I wrote it wrong. This is why. So g over 9, that's the acceleration, and h does actually multiply. Yeah. All right, I think that's all good. So I have so there, that's meter square per second squared. Squared is good. Here I have meter squared per second squared. Square root is meter per second, and I'm gonna be dividing by r, so I'll get 1 over second. Yeah, I think that's all good. How much time do I have? I have 2 minutes. Okay, so I think that's enough time to attach work. So let me attach work. So starting with the A. Let me just grab as much as I can here. And of the part B, I'm doing that. And finally part C. All right, so let me submit at end, and oh, I guess in the mode I'm in, there's I can't quite check if I made any mistakes in the answer. Let me do this. I'm pretty sure I didn't make any mistake, but just to be doubly sure, let me go into my Open Math as instructor and figure out and show up the answer key and compare it side by side with the answers that test student got. All right, so this is the attempt that test student made. I can change the scores if things warrant, but mainly what I'm interested in is the answer key. So answer key, yeah, shows those two forces. That's it. Tension in the string. Let's hope it's 8/9 mg. Because if that's wrong, oh, I need to click evaluate. Okay, 8/9 mg, good. And then how fast is it falling in with the 8/9 mg? A square root of 2 over 9 gh. Square root of 2 over 9 gh, good. And omega is, if you're absorbing this, that'll be 4 times 4, 16 times 2 is 32. 32 over 9 times gh over, yeah, r squared, bringing that in, it becomes r squared. All right, so I think I did it all right. I guess I must have done, oh, yeah. So what the answer key does, that's the longer way to do it. What I did when I'm actually in the time, under the time limit, that's the correct way to do it, in the sense that it's going to be the quickest. And it doesn't involve any potential confusion in physical concepts.